Welcome. In this tutorial I'm going to show you how to use the new inverse kinematics function within Real Virtual I/O Professional. With the inverse kinematic you can make a robot move based on targets and paths. You define how the tool center point of the robot should move, and you don't need to move anymore the axis itself. I'm going to show you how a robot needs to be prepared for being used with the inverse kinematics, and I'm showing you how targets and paths can be defined. Please note that the inverse kinematic function is only available in Real Virtual I/O Professional and not in starter version. Something very important to note is that the robot, the industrial robots, needs to be in a certain manner, so there are some limitations, so you can't do the kinematics for each and every robot. So one limitation is it's always a 6-axis robot with just rotation axis, and the robot needs to be described or describable by all these geometric parameters, so A1, A2, B, and the dimensions C1, 2, 3, and 4. And one very important point is that the robot needs to be able to align axis 6, 5, and 4. So the rotation points of all this axis needs to be aligned, or the robot needs to be able to align them. And that's, for example, not the case for UR robots. So the inverse kinematic is working for most of the industrial robots, but for the UR robots, for example, it's not the case, because the UR robots are not able to align the axis like that. So let's start. First of all, we are going to import the CAD file of the robot with CutLink. So I downloaded from Stäubli a CAD file. I'm setting the quality to medium. I don't need the top assembly node, and I'm importing the CAD file. Here it is. So let's move the robot to the right position. And my advice would be also to position it for preparing it at position 0, 0, 0. And I'm now exporting it as an FBX file, so that the 3D mesh is not only available in the scene, so that it's also available in the assets. And by doing this, I'm getting a reusable 3D file, so I can use it later on for prefabs. Delete this, and I'm going to put the prefab now in. So put it again to 0, and first of all, just as a helper, I'm placing here also at 0, 0 a right-handed coordinate system, which we prepared as a prefab. And I'm going to turn this robot so that the right-handed coordinate system, the x-axis, is pointing towards you if you're standing in front of the robot. So in this imported prefab, we have got all the components, the different axes of the robot, but they are not structured in the kinematic chain. And maybe the axes are also not aligned as we need it for the inverse kinematic. And that's what we are going now to prepare. We are now going to put the full robot and the kinematic chain into a new empty game object. Let's call it like the robot. And now we need to rotate the basis coordinate system of the robot into a certain manner so that the x-axis is pointing towards us, the z-axis is pointing upwards, and the y-axis, the unity axis, to the left-hand side. Now I'm creating empty game objects for all the axes. So, and I all put them for the moment to 0, 0, 0. And let's name them axes 1, 2, 3, 4, 5, and 1 is missing. So let's add axis 6. And what we can also do, we just add drives to all these axes. And for the moment, we don't do anything with the drives. So for the moment, we have an empty structure with the name of the robot at 0, 0, 0 with a base game object oriented like this. So X forward, Z upwards, and Y to the left. And we are having 6 empty game objects, all of the game objects at 0, 0, 0, non-rotated, with the name axis 1 to 6. And we added 6 drives to it, but for the moment we won't use them. If we now look into our prefab of the robot, which is still in parallel, we see that all the components are not in the kinematic structure yet. So that's how we imported it over the CAD interface. And we have some rotation points here. And that's the case for the pivot points, maybe in the rotation points. That might be the case for Stäubli, but it's not the case for all of the robot. It's very dependent what kind of CAD files you're importing. So my advice would be now to put the position on the axis to the positions which you can, for example, read out of the data sheet. So let's get the data sheet of the Stäubli robot. So here it is. I downloaded it from the Stäubli website, the data sheet of our TX2 160 robot. And what we need for the moment is this here, because in this technical design we can see the position of the axis. For axis 1, our rotation point will be in the origin point of the robot. So let's go directly to axis number 2, and in here we see that axis number 2 is in the height of 550 millimeters, the rotation axis. And we see here that we have got a distance of 150 to the rotation points of axis 2, 3, and 4. So this measure here. Let's get back to Unity. Axis 1 is and must be in the robot origin. And for axis 2, we have the values which we can take out of the technical design. So the height in Z should be 550 millimeters. So 0.550 in Unity. So that's meters. And for getting the rotation point in the X direction, we are taking out of the technical design this 150. Not Y, it needs to be the X, 0.150. So by that, we defined axis 2, and we'll continue this for axis 3. Looking into the data sheet, it's in the height 0.82 in relation to 5 in relation to the axis 2. We are now going to do this in fast forward mode for all the axes. So we take the values out of the datasheet and we are going to position the still empty game objects to the positions where they need to be. So the 0 point of the axis needs to be in the rotation point. So we now defined all the axes, and the rotation of all the game objects is 0. So same oriented as the base coordinate system. Now we have to move the meshes to the still empty kinematic structure. It's still prefab, so let's unpack it first so that we are able to move these meshes. And let's go through. So this is axis 6. That's axis 5. This one here is axis 4. This here is axis 3. This is axis 2. This is axis 1. And that's the basis. We put it here on top. So axis 6, 4, 5, 4, 3, 2, 1. And now we have the rotation points in like we have it in our data sheet. What's still missing is that our drives here, which are connected to the axis, are not defined concerning the direction. And the direction needs to be always based on the right-handed coordinate system in the positive direction. So axis 1 is a rotation axis. It's on the rotation Z, and positive direction is this direction, so we need to invert it. So that's the positive direction if it rotates around Z. And like that we do it for all the axes. That's the positive direction. Okay, 3. That's the positive direction. 4. Like that. No, rotation set. Also here it needs to be inverted. 5. Needs to be like that in positive direction with the right hand rule, and this one is rotation set, and it needs to be reverted based on the right hand rule. So now we defined all the axes with the directions. After we define the drive directions, we also need to define the limits of the drives, and for this we are going back to our data sheet, and we are having here the limits of all the axes, and we are also having the maximum speeds in degrees per seconds for all these axes, and we are going to put these values on the drives within Game for Automation. So for axis 1 we are going to use limit. You always we use acceleration, and for the acceleration value I don't have ones for Stäubli, so I'm just putting in here 1000. And for the limit of axis 1 it's plus minus 180, so 180 to 180, and the maximum speed we put it in here to target speed is of axis 1 240 degrees per second. And like this, we are going to do this for all the axes. So I did this without recording, but you see here, for all the axes, we are having limits, upper and lower limit, and the maximum speed and an acceleration for 1000. Put it in. So we are nearly finished in preparing the robot, but what we now need to do is we need to add here the inverse kinematic script, which is going to control the robot. So under game for automation, add component, robot IK. The IK script, robot IK script, always needs to be put it on the root of the robot. And here we need to assign now the 6 axis. So we just drag and drop in here our 6 drives. 3, 4, 5, and 6. So this we don't need. And you see here the option elbow in Unity X. So currently in this design here, the elbow is upwards. So it's not in Unity X, it's in Unity Z. So we don't need to turn that on. But we also need to define a TCP. TCP is just an empty game object here on the last axis. So let's put and the TCP always needs to be aligned like that. Same alignment as the root. So set upwards, X in the forward direction and Y left. So here we put this TCP in. And now we can push on, or we must push on calc kinematic parameters. And we are going to have all the kinematic parameters which we had in this design. So this design here, all these parameters which we are having here are now calculated automatically, and our tool offset, because it's directly currently without a tool on the last axis, is 0. We can now start in defining targets and paths. I'm creating an empty game object. Let's call it paths or path. And here, let's add the path script. Add component path. One thing which is very important, the path always needs to be underneath the root of the robot, where our robot IK script is, as a child game object. And here in the path, we still don't have any targets defined. So let's add a new target to the path. Automatically an empty game object is created. And as you can see here, we are already able to move the robot by moving this game object. And because follow in edit mode is on here, we are getting a preview of the position. And if we can't reach the position, a red sphere is shown. Yeah. And there are several solutions for the robot. They are shown here. So there are several ways for reaching this position. And we have 4 possible solutions and another 4 solutions which are not possible because access limits are reached. And we can switch the solutions here. If we are selecting a non-possible solution, we are getting again the red sphere. So we can select one of the first solutions. Let's take this one. So we are having currently one target. Let's put it there. And by pushing Control, if the path is highlighted, we can rotate. Or we can use the normal rotate functions if we select the target. So we can edit the target while the path is selected, and you will see after adding all the targets we see multiple targets, or you can edit the target in edit mode while the path is selected. Let's add a new target. So add a new target, and the new target is automatically put it at the end at the same position as the last target. So let's move it. Add a new target. Let's add another target. Let's put another target. Move it. And as you can see, we have defined a path. So currently all these movements are yellow. That means that they will be done as a point-to-point movement. On the path, we are setting start and loop. This will mean this path will be started when we start the simulation and looped, so it will be restarted automatically. So let's see what's going to happen. So the robot is following the path, and even if it looks like a linear path, especially at the end, you will see it's a point-to-point path. And for the path, we can also do a speed override. This will slow the path down. And if you look at in very detail, you will see that it's not a linear movement, even if it looks sometimes like that. It's, especially here you can see it, it's a point-to-point movement. If we would like to have linear movements, we can select all the targets and say, okay, this should be a linear movement. Let's start it again. So now the movement will follow exactly this line. You will see it here especially. Now it's a linear movement. If it's a linear movement, the linear acceleration and the linear speed are defining the speeds. So for example, for the last target, we could increase the speed and maybe also the acceleration. And you will see that here the last target will be much faster. Okay. We are nearly at the end of our tutorial. So we learned how to define these paths. And if you select the path, you can edit all the waypoints. We've got a preview in editor. When pushing on Control, you're even able to rotate it here in edit mode. Maybe last thing to add is how you can connect it to logic steps or to external PLCs. So we are having here start conditions for the path, and you can assign PLC output bool signals to start this path, and as well you get a status spec, a PLC input bool if the path is started or if the path is ended. And you can connect another path, so a second path, and start the second path directly after the first path. So that's it for the moment concerning our new inverse kinematic function inside of Real Virtual I/O Professional, and have fun in using it.